here's example 3 of finding all the rational root theorem of this given function. Now this polynomial has a degree 4. So same as usual, the first step is using the rational root theorem and crank out all of the possible rational roots, which are in the form of the ratio of the positive and negative factors of the constant over all the positive and negative factor of the leading coefficient, which is invisible positive 1. So all of the positive and negative factors of the constants, positive 30, is going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30 over all the positive and negative factors of the leading coefficient positive 1, which is just plus or minus 1. Taking each number in the numerator and set it over positive 1, we will know that all of the possible rational roots, x equal whatever, is going to be x equal plus or minus 1, plus or minus 2, plus or minus 3, and so on. Just like that. So these are all of the possible rational roots of this function. Now the next step is to see which one of these x value would give you the remainder 0, and that remainder is from the remainder theorem, and we can find that remainder by taking that x value that we select and plug it into the function. As usual, start out with the lowest the lowest x value, which is positive 1. So if x equal to positive 1, which will give us the corresponding binomial equation by subtracting 1 to the, moving 1 to the side of the x. That corresponding binomial equation is going to be x minus 1 for this x value that we select. So if x equal to positive 1, then by the remainder theorem, we have the remainder of f of positive 1 equals to what? Well, let's see. 1 raised to any exponential power is going to be 1. So we got 1 plus 1, which is 2, minus 11, which is negative 9, minus 5, which is negative 14. Negative 14 plus 30 is going to be positive 16. But the remainder positive 16 is not 0, so by the factor theorem, x minus 1 is not a factor of this function. Well, let's try the next one. If x equal negative 1, which will give us the binomial equation of x plus 1 equal to 0, and of course just add 1 to the side of the x and we get x plus 1. Then by the remainder theorem again, the remainder f of negative 1 is going to be negative 1 raised to the 4th plus negative 1 raised to the 3rd minus 11 times negative 1 raised to the 2nd minus 5 times negative 1 plus 30. Like that. Negative 1 raised to any even exponential power is going to be positive 1. So we know this is positive 1. And this right here is negative 11 times positive 1, which is just minus 11. Negative 1 raised to any odd power is going to be negative 1. So this is minus 1. Yeah, because negative 1 raised to the 3rd is negative 1 plus negative 1 is minus 1. Negative 5 times negative 1 is plus 5. And then bring that to plus 30. Let's see, 1 minus 1 is 0. Minus 11 is negative 11. Negative 11 plus 5 is negative 6. Negative 6 plus 30 is going to be 24. But the remainder 24 is not equal to 0. So by the factor theorem again, we know that x plus 1 is not a factor. Is not a factor of the function f of x. Well, let's try the next x value of positive 2. Well, if x equal to positive 2, which will give us x minus 2 equals 0. Then by RT again, remainder theorem, the remainder f of 2 will be equals to 2 raised to the 4th plus 2 raised to the 3rd minus 11 raised to the 2 raised to the 2nd power minus 5 times 2 plus 30. Let's see. 2 raised to the 4th is positive 16. 2 raised to the 3 is going to be positive 8. 2 raised to the 2 is 4. Negative 11 times 4 is going to be negative 44. Negative 5 times 2 is negative 10. And then bring down to plus 30. Let's see. 16 times 8 is 24. 24 minus 44. 24 minus 44 is going to be negative 20. Negative 20 minus 10 is going to be negative 30. But hey, negative 30 plus 30 equal to 0. So with the remainder being 0, when f is evaluated at x equals 2, we know that x minus 2 is a factor of f of x. So by ft, which is factor theorem, x minus 2 is a factor of f of x. That means we get to rewrite f of x into the product of x minus 2 and this other blank factor. This other blank factor is again something that can be found by setting up the synthetic division. And the synthetic division is going to involve the x values that gives you the remainder 0 that you used the remainder theorem to find earlier, which is positive 2. So x equal positive 2 is a divisor. And the dividend of the synthetic division is just all of the coefficient of the original function listed in the same order from left to right. So we list positive 1, negative 11, negative 5, and 30. Of course, first step is to always bring down the leading coefficient positive 1. Now, divisor 2 multiply 1 is going to be 2. 1 plus 2 is 3. 2 times 3 is 6. 2 times 3 is 6. Negative 11 plus 6 is negative 5. 2 times negative 5 is negative 10. Negative 5 plus negative 10 is negative 15. 2 times negative 15 is negative 30. 30 subtract itself is going to be 0. So this other factor is going to have the coefficients of 1, 3, negative 5, and 15 from the quotient right here. What goes in between? What goes in between is going to be all of the x variable, except for the last one, because the last one is going to be the constants. But it's not just the x. We're supposed to put the exponential power for each of these x. And the exponential for each of these x is still going to be in the same decreasing order from left to right. But instead of the degree 4, as in the original function, we're going to have to bump it down by 1 unit. So the degree of this other factor is going to be 3. And then, of course, this is going to be 2. This is going to be 1, which we don't have to write it. And then we got a constant. We got positive 1, positive 3, so that's plus. We got negative 5 here, so that's the minus, so right there. And then negative 15, so I forgot to put a minus. So this other factor is x cubed plus 3x squared minus 5x minus 15. And then it has to be equal to 0. We have the factors x minus 2, and we have this other factor here. This other factor has a degree 3. Now, usually when we see a factor of the original function with degree 3, we have to ask ourselves, do we have to repeat the entire rational root procedure as shown up here, but just for this one? Or can we factor by group? Usually the first thing you want to try to do is to factor this factor by group. And in this case, fortunately, it is actually factorable by group. So let's call this one g of x. So g of x is equal to x cubed plus 3x squared. And instead of writing minus 5x, I'm actually going to change it up a little bit. I'm going to write plus and then minus 5x. And of course, remember that the minus side is the same as plus, negative, like that. Instead of writing minus 15, I'm going to write plus minus 15. And the plus side is going to help us a lot with factoring by group. And you guys know how to do that. To factor by group, put the first two terms inside the parentheses like that, and put the last two terms inside their own parentheses. In the first binomials here, we see that we can factor out the x squared. So factoring out the x squared, we're left with just x and then plus 3. For this binomial, we get to factor out the greatest common factor of negative 5. So we got plus minus 5. After factoring out the negative 5, we're left with just x and then plus 3. Yeah, because if we were to distribute negative 5 back in, we got negative 5 times x is negative 5x. Negative 5 times positive 3 is going to be negative 15. So hey, this is a factor 4 of that. But guess what? The term x squared is multiplying x plus 3, and the term negative 5 is also multiplying x plus 3. So factoring out the x plus 3, we're left with just x squared minus 5 in here. So g of x can be factored out to this one. So that means, oops, I'm moving it around here, sorry about that. F of x is actually equals to the factor x minus 2 multiplied by the factor form of g of x, which is right here. It equals 0. Of course, x squared minus 5 cannot be factored out anymore, so using the zero product property, set each of these binomial factor equal to 0, and then we solve for x. X minus 2 equals 0, so we know this is going to be x equals 2. This is going to give us x equal negative 3. Solving for x squared by adding 5 to both sides, we get x squared equal positive 5. Getting x by itself by getting rid of the second exponential power by taking the square root of both sides. We know that x is going to be equal to plus or minus square root of 5, and this is going to be like plus or minus 2.236 something, like that. So hey, this is the final answer. So all of the rational zeros of this function are all of the x values in the box here.